Here's our bell work. Just got to combine some like terms, and we did a problem almost exactly like this in class last time. Or I guess it was a 1.4, right? So I start, and I see this first term here on the left, because I always start on the left, and I have an x term. So I need to find all the other terms with x's and then combine them, okay? So that's a positive 4x's. Remember, even though this term has an x, it's an x to the power of 2, so it's not considered a like term right there. And so the next one I see would be this negative 13x, then a negative 5x, then a positive 4x, and this one on the tail end of this, that's a positive 1x right there. So I'm going to combine it with my other x terms. Now, since they're all x's, I'm just going to take the coefficients and just combine them. So that'd be 4 minus 13 minus 5 plus 4 plus 1. And that gives me negative 9 x's. So that takes care of all of my x terms. Now the next term I see is this constant term, just a regular number. So I'm going to start combining these. That'd be 8, negative 7, positive 4, and negative 6. So let's combine those. 8 plus 7, minus 7. There we go. Plus 4 minus 6. Enter. And I end up with 3, which is positive, so I put this down as plus right there. And then all the other terms that I have are x to the power of 2 terms. So I'll do these ones in green. And so I'm looking for any x to the power of 2 terms. There's 2 of them. There's negative 5 of them. There's 6 of them. And then again, there's a 1 right there, 1 of them. Okay. So combine those. 2 minus 5 and plus 6 plus 1. Enter. That's positive 4. So we show this positive as plus 4. 4 times x to the power of 2. And of course, there's many different ways you can actually write this, but this is the order that I have it in. Again, as long as the signs are the same for these, then you're in good shape, because you could have written this as, for example, 3 minus 9x plus 4x to the power of 2. It's up to you. All right, there's our objective. I can solve equations with one principle of equality. Take 30 seconds and copy that down on the classwork, please. And yes, you guys did do this in 7th grade, but 7th grade is a long time ago, so, and since it's not really applicable to life, you probably haven't used it in a long time, so we're gonna have to go over this stuff again. But the good news is right now we're starting with very small equations. We'll work our way up to bigger ones, bigger stuff that you saw probably in 7th grade, but we'll work our way up to that, okay? So to understand what we're solving for when we look at these equations, it's going to say something like solve for x or just solve even. What it's really asking is what value of x makes the equation a true statement. And that's what we're looking for here is truthfulness, okay? What you'll find with these equations is that there's actually an infinite number of values that would make it a false statement. We're looking for one value that makes it a true statement, okay? For example, if I told you that 20 equals 20, you'd be like, hey, that's a true statement right there, okay? And hopefully everyone knows that's true. It's true for now, although there are curriculums that may be changing that in the future. But it's true for now, okay? So, but if I told you, hey, look at 10 right here. Is this equal to, I don't know, 29? And you can even put a question mark right there if you'd like. But no, that's false now. And hopefully we know that's false because these are not the same. In fact, even if I change this, there's 29 right here. Let's change that to not just 10, but let's change it to negative 10. That is still a false statement. And while they may look the same, and they're even the same distance from 0, they're in opposite directions, so they're not actually the same thing, right? And if you think about this in terms of money, one's positive and one's negative. You can either have $10 or have owed $10, and hopefully you'd rather have $10 there, but they're definitely not the same thing, okay? So we're looking for values of x that are going to make these statements that we're going to be seeing, that are equations, we got to make them true. So this one is x equals 10. This is about as basic as you can get, and this is really what our answers will look like in the end. But I just want to emphasize that it's about replacing the x with a value, just like we did in lesson 1.3, where we were solving or evaluating expressions. So you can replace numbers with letters, right? And so if I looked at this equation and I replaced x here with 10, then the statement would show 10 equals 10. And as it turns out, is that true? Yeah, that's true. Okay, so that means that if I replace x with 10, then I get a true statement. So here's our first one. And while we do have actual mathematical strategies to solve these, I just want to emphasize the idea that we need a value of x that makes the statement a true statement. Okay? So for right now, it says x plus 2 equals 10. What is the solution to the following equation? So again, this statement right here is really saying what value of x will make this true. And while some of you, I mean, you may look at this and you may think, well, maybe you know this by heart, like you can do this in your mind. Again, we'll have some strategies to do that, but most of you, I think, know that x in this case would be equal to 8. And that would make that a true statement. So right now we know, or we think, that x is 8, but we can actually check in the equation, right? We can say, well, look at the equation, x plus 2 equals 10. That's the original statement, so it should be true every time. But let's replace that x with an 8 and see if it's true. So I'm putting a question mark over the equal sign, because I'm not sure if this is actually true or not yet. I mean, of course, I think some of you do, because you can do that pretty quick in your head, but 8 plus 2 is 10. And when I check this, I see that 10 equals 10, and yes, that is actually a true statement, okay? Now, since I did that, and I checked it, I can box that in with a lot of confidence, knowing that my answer should give me full credit right here, okay? Now, I won't check till later, but for now, just look at this problem, right? It's x. X represents some value. We don't know what value, but some value. You're going to take away 4 from that value, and then that should give you 10, okay? Now, again, some of you look at this and like, dude, I already know that x, if I replaced x with 14 right here, then I would get a true statement, right? And so this is really how we want to write our answers for these. X equals 14, meaning this statement right here tells us if I replace this x with this number, I get a true statement. Okay, and we can check that, just not actually showing, but 14 minus 4 does equal 10. Yeah, that would be a true statement. And then again, we can box that with some confidence. All right, what about 5 times x equals 10? Well, 5 times something equals 10. So if I needed to replace x with something, what would that be? I'd have to replace x with 2 in this case. 2 would make that a true statement because 5 times 2 is 10. That would be a true statement, okay? And then, of course, we see some division right here. X divided by 2 equals 10. So what value divided by 2 would give you 10? Well, that means you'd have to replace the x with 20 right there. Again, you can just check offhand. 20 divided by 2 is 10. Yep, that's a true statement right there. Now, again, some of these I think you'll be able to do in your head, and that if you can, that's great. It's not required that you do, but again, we're going to show you some math principles that will always give you true statements, and it gives you a little bit more that you can do with equations with some math backing on this stuff. Now, for all the 4 problems that we did, before we move on here, for all these 4 problems that we just did, x equals 20. 20 divided by 2 equals 10 in this one. Can you think of another value that would make this a true statement? Now you could continue to think, I mean, would 28 work? No, of course not. That'd be 14. And what about negative 20? No, that'd be a negative 10, so that's still not good. What if you made it 200? Does that help? No, then you get 100 instead of 10, okay? My point here is that there's a lot of values of x here that you could replace, but it would not be true. It will give you very false statements if you replaced x with anything but 20 in these cases. Okay, so right now, when we solve these, we pretty much should expect there to be just one solution to these problems, okay? Eventually, though, of course, a little bit in this grade, but mostly in 9th grade, you're going to see that it is possible to have 2 answers, but for now, just one. So mathematically, we use what we call principles of equality to solve equations. Now, these are called one-step equations, and that's kind of our objective today. Can I solve an equation with one of these principles of equality? And so, while it's using letters here, it's very abstract, which makes this algebra, by the way, not that I think anyone cares. But if you said, hey, I got something that equals something else. Sometimes these are numbers, sometimes they have numbers and letters, they're expressions. This can be an expression and that can be an expression. But they look different to start out with. It's the equal sign that gives us some balance on this, okay? But here's the thing. If you took this A and B and then you added a value to, let's say, A right here, and then you force this in. So this is you putting something in there. If you do it to this side, you have to do it to the other side. I think that's usually the way that 7th grade teachers kind of present that. Whatever you do to one side, you have to do to the other side. And these are operations. You can add something to one side as long as you add the same thing to the other side, okay? Same with subtraction, same with multiplication, same with division. And so why would we do this? Well, it's going to simplify the equations for us to make things a little bit easier. Now today we're looking at one-step equations, so we should only need one of these, but in the future, we may end up having to use 3 or 4 of these at a time. Okay, depends on how big the problem is. But the objective for these, starting with addition and subtraction, and again, this is where you take control of the equations, not the other way around, because yeah, if you don't take control of them, as it turns out, they will destroy your lives. And I've seen that with my college students. It's unfortunate. It's not very pretty either. But with addition and subtraction, you need to make a certain value, and with addition and subtraction, you're trying to make zeros with these principles of equality, okay? If you can force a value to be 0, here's the great news. You can ignore it. Pretty much like you would with a person. Not that you should. But when you see zeros, ignore it, okay? And that means that we're going to make it a phantom 0. Well, that's for addition and subtraction. But if you look at multiplication or division, this is where we try to make, it's the only other phantom value we have really is phantom 1s, okay? So we use multiplication to make phantom 1s. We use division to make phantom 1s. And specifically, when we try to make 1s, we're usually looking at the coefficient. Remember I said I was going to use that vocabulary quite a bit, coefficients. So it's not just that we're trying to make 1s. We're usually trying to make the coefficient a 1. In that way, we can make it a phantom 1. Okay? Now, making zeros, again, this is not for the coefficients usually, but they may be for x terms, which we may see, but just probably not today. So here's our first problem. And again, I think some of you look at this and like, Mr. Sal, what the crap? This is so easy. That's fine. We want to build our way up, just making sure that we understand this stuff. Because if you can't do this with one principle of equality, it's not likely that you can do it with 3. So we got to make sure that you guys have this stuff down. Okay, so 18 equals 27 plus b. And again, some of you could do this in your head. I'm still going to use the math principle of equality. Okay. Now, the principles of equality, before I do this one, what they're going to do is maintain equality, but they're going to change the way the problem looks, okay? So on this problem, here's the way I like to set up my principles of equality, okay? It gives me a line right here, so I can look at the right, and if I do something on the right, I got to do it on the left. Or if I do something on the left, I know I got to do it on the right. It's just an organizational thing, okay? Now, here's what we need. We need the V. And it is a phantom 1v, by the way. We just need it to be v equals something. That means that the 27, I don't want it there. So how do I get rid of 27? I need to make it a 0. Well, remember from the last slide, the way we make zeros, we either with the addition or subtraction principles of equality. So I'm going to take that 27 and I'm going to, subtract it from itself. That is how I will make it a 0. Okay? But again, the principle of equality says if you do it to this right side, you're going to have to do it to the other side as well. So minus 27 here, okay? Now, for those of you who are like, man, I don't know how to do 18 minus 27. That's okay. The calculator does. So just put it in the calculator. 18 minus 27, boom, negative 9. Okay? Now, see how we did one principle of equality, and this is solved. It tells us what V should be. But is there a way to make sure that that is the actual value of V? Yeah. Let's write the original equation. 18 equals 27 plus v, right? But right now, I think the v is negative 9. So I'm going to replace it with negative 9. And I will check to see if this is true. So I put a question mark over the equal sign here, okay? So what is 27 plus negative 9? Put in the calculator plus negative 9. You can use the parentheses if you'd like. And before I push enter on my calculator, by the way, I should expect to see an 18. If I don't see an 18, I know I made a mistake somewhere in here. Maybe I just even wrote it down wrong, or maybe I even typed it into the calculator wrong. Those are my most common mistakes, but maybe they're different for you, okay? So when I push enter on my calculator, I do see 18. And so the check is, does 18 equal 18 right here? Yeah, that's a true statement. Since that is true, I can go back up to my original solution. Remember, a solution makes it the original equation true. Yeah, it made the original equation a true statement. And now I know that this is the solution. So I can box that in with a lot of confidence, actually. All right, here's the next one, okay? Negative 27 equals b minus 48. So this one sets up a little bit different, but we're still going to be using principles of equality to solve these, okay? And we should only need one because these are one-step equations. So here's my setup, right? So I got my line to represent the sides. Whatever I do to one, I got to do to the other. And for some students, they even say, well, it's kind of like an arrow right there. It brings the equal sign down. Yeah, sure. If you want to look at it that way, that's fine. But the b right now, I got to drop it. That's what I would really like to do anyways. I would just like to see it by itself. I don't want this minus 48 with it. So get rid of it. Okay. How do I get rid of? This would be, as a term, negative 48. How do I make it a 0? How do I get rid of it? Yeah, it's to make it a 0. So let's add 48 right there. Now I'm circling this. Or some people think that that's a circle. That's a 0 right there to show that what I did with that negative 48 is to make it a 0. It's just if you do it to one side, please, you have to make sure you do it to the other side. Otherwise, you have changed the actual original equation. And then you will get a false statement, okay? So what is this? Negative 27 plus 48, enter. Yep, I got 21. So right now, I think b is 21, right? So once again, I just want to check, and it shouldn't take very long to check these, but negative 27 equals b minus 48. I'm checking for truthfulness, so I'm going to replace the b with the value of b that I found, 21. And I will put a question mark over the equal sign, okay? Because I don't know if that's true or not. But 21 minus 48, let's put this in the calculator, enter. And yeah, just what I expected to see, negative 27, that's what I saw. And negative 27 does actually equal negative 27. That's a true statement. So now I can go back to my solution and box it in with great confidence. All right, this one. Now some students are still getting a little confused right now. They're like, well, what the crap operation is this? That's multiplication right there. Okay. Now, it's not really important that you see the multiplication, but if it helps you, then you can put it in there. Okay. But what I would like here is not just x, or negative 9x's. What I'd really like here is 1x. See? Like I said, the two principles of equality that we use to make ones are multiplication or division. All right, so how do I make that negative 9 coefficient a 1 coefficient? Well, just take, the only way you make one is usually just to take a value and just divide it by itself, like this, okay? So see how I divided it by itself? That's negative 9. You kind of see this repeating pattern. Whenever we make zeros or ones, we're kind of using the same value. Just sometimes with addition and subtraction, we're using the opposites, right? So negative 9 minus 9 right there. Yeah, that's going to give us that 1. Well, what does this equal? 36 divided by negative 9. Put that in the calculator. Boom, negative 4. Now when I write my answer, I won't use the 1. I'll make it a phantom 1. By the way, that 1 is still there. It's just lurking in the shadows because it's a phantom 1. And that kind of makes phantom values kind of creepy, but they're there. So, can we check this? Yes, we can. Negative 9 times x should equal 36. That should be true. And right now we think that x is negative 4. So let's replace it with negative 4. I'm just going to put it in parentheses so that we know it is multiplication. And I will put a question mark over the equal sign because I don't know if it's true. Negative 9 times 4 is, you guessed it, positive 36. So this equals 36. And that is a true statement. So now I can box this in with confidence. The negative 9's right there, they became a phantom 1 right there. That's where I get this 1 right here. Negative 9 divided by negative 9 is 1. But again, sometimes it's shown as crossing these out. or like canceling these out. It's not crossing them out with just a cross, but it's a 1. Right there. It's a phantom 1. Okay. All right, this one's a little different. By the way, that fraction line, which we did talk about, that's division right there. So if you need to know that, then do it. But take 30 seconds, try this one out, then we'll go over it, okay? 30 seconds. So on this one, that's divided by -7 right there. Here's what I'm going to do to solve this one. I'm going to multiply this by, well, -7. This is what we call inverse operations. But this w divided by -7, if I multiply it by -7, some people like to see this as a fraction like this, which then makes it a cross simplification problem. Now, I cross these out. I can cross them together like this. When you cross these out, it's not that you're just canceling them away. Something happens to these -7s right here. That really becomes -7 divided by -7 right there. Thank you. So, -7 divided by -7, what is that? It's 1. Now, this is a slanted 1. That's okay if it is. But just like the last problem that we saw. So, that becomes a phantom 1, and what am I left with? Now, you could show this as w over 1, like this, but anything divided by 1 is itself, which we've seen, that principle. So, w then would equal, yeah, guess what? I see how I multiplied by -7? You got to multiply by -7 on the other side, too. That is the multiplication principle of equality. If whatever you do to one side, you got to do the other side. That's all the principles of equality. So I got to do -4 times -7, which is, that's going to be positive 28. So I see now that w will equal positive 28. Let's just go ahead and do a quick check. And I know some of you can do that in your mind, but let's show the work on this. W over -7 equals -4. But I'm now replacing the w with the value we found, which was 28. All right, now you can use the fraction button to put this in, but whatever I get from this, it should equal -4. So there's my question mark. You could just use straight division if you'd like. 28 divided by -7, it's going to give you the same answer. When I put this in the calculator, I get -4. And that, by the way, is true. Okay, so now I know that w equals 28 would make that original equation a true statement. I can't emphasize this enough. If I got something other than 28, when I go to check this, I would see that -4 would not equal this -4. That would give me a false statement if I did anything but 28 right here, okay? So you can check, and if you ever get a false statement, don't just leave it like that. Go back and just see, maybe here instead of multiplied in the calculator, you put divided by. Okay, or like right here, then you would have gotten 4/7 or something like that. Maybe you did the wrong operation. It was like addition. You did addition instead of multiplication. Okay, but if you'll just check these, you'll always know that these are true. And so in the past, students come and they're like, "Hey, Mr. Sal, is this right or wrong?" You tell me. You tell me. Check the answer yourself because you can, and the calculator will even do that work pretty quick for you. Okay. There is a difference between equations and expressions. Equations have an equal sign. Expressions don't. Okay. So actually, equations are made up of two expressions that are equal. Sometimes it's just x equals 5. This, by the way, is an equation. You can have single term expressions, so it doesn't have to be very big, like a -5 and 10 minus 5x equals 5. So it doesn't have to look like this, okay? But this is still an equation, but it doesn't have to look like that, okay? So again, equations have the equal sign, expressions do not.